Hi friends, unlike traditional models that rank stories, today we're going to talk about a paper from Kuaishou, where they apply Uplift modeling to make decisions on resource and strategy allocation. Here's the problem setup. In the recommendation system, there are different types of content. There are content that the system already knows the user are interested in. We call them familiar content. There are content that the recommendation trying to understand if the user will like. They are exploratory content. And also there are promoting content such as ads and shoppable items. So apparently you can see the trade-off. For each request, you can only send so many stories. How do you decide the proportion of content to show to the user? As you can see, there are clear trade-offs. If you keep sending a lot of familiar content to the user might get fatigued. If you keep sending an impressing exploratory content, the user might not be actually interested. And you keep showing ads to people, and they might just leave the app. So as you can see, there need to be a strategy that gives the perfect mix of different types of content and show it to the user. So this is a problem that this Kuaishou paper is trying to solve. So here is a big picture of how Kuaishou solved this problem. They dissect the problem into two components. One is the offline uplift modeling. The other is the online value estimation. So the uplift modeling essentially models user sensitivity to each treatment. For example, here, it is predicting the expected response of applying treatment and applying control. So usually, by calculating the delta, you will know user sensitivity to this treatment. For the online component, the model estimates the user's value weight. In other words, the user's preferred response. For example, of all the positive response, usually the user will do like 50% of watch, 30% of click, and shop 20%. So with the offline part, we get the user's sensitivity to the treatment. With the online part, we get user's preferred response. Together, we calculate a weighted sum that gives a final score that summarizes the reward of this treatment to this user. If this final score is greater than a certain threshold, we apply the treatment. Now let's take a closer look at the offline uplift modeling part. Essentially, it takes two types of features. One is user feature, the other is treatment features. With this feature encoder here, we turn all the features into embedding. And the feature selection is essentially a target attention that select features corresponding to the treatment. So as you go upward, you can see there are multiple branches. If we have 10 treatment, then we'll have 10 branches. In each branch, as you can see, it is predicting two things. First is that what is user's response if they apply the treatment? So it's YRK. And also it is predicting if they don't apply the treatment, the control part, what is the expected response. And each branch will predict a pair of response. So you see this problem here. All these branches, they share the same control expert, and they're all predicting what is user's expected response if they don't apply any treatment, which is a control component. So it might diverge, right? Each branch might predict a different result for the control. So how does Kuaishou solve this? They applied KL divergence. So as you can see in the loss function here, it is not only just a mean square error, it applies additional KL divergence loss. In the KL divergence, it compares the probability distance for each branch versus the mean of all the control component prediction. This is a mean because it divided by K. Z is the scoring of the predicted control response. And this is for the K prime. Essentially, with this KL divergence component, you make sure that all the branches, their predicted controlled response are converging to the same. And the next is the online component, where we estimate value weight. So what is value weight, you might be asking? It's about how many positive response do you have. For example, we care about users' long watch, subscribe, and shop actions as response. For each request, we'll log users' such positive response. And in this value weight estimating, we'll be estimating the number of different types of response, long watch, subscribe, and shop for each request. So essentially, you may ask, why do I care? So if given this contextual features and given all those candidate items, the user has zero likelihood to shop, then in this case, then there's no need for us to show any shoppable items, even if the shoppable items sensitivity is high. So if the user just never shop, they always long watch, subscribe, then in other words, it just doesn't make sense for us to show to the user any shoppable items. This is the rationale of having this value weight estimating. So now, putting it all together, what is so special about uplift modeling? The essential key is that you not only model user response based on the treatment, you also model user's response based on the control, and you use the delta to determine user sensitivity to this treatment. So if the user response is the same regardless of control and treatment, then that means there's no point on applying this treatment. So this is how Kuaishou is trying to model this, because there's only so many stories you can show to the users. Using uplift modeling ensures that we don't waste the impressions. The other innovation here is the value weight estimating. It is estimating in this request, given all those candidate items, what is the percentage of different types of positive response a user might have. So in this value weight estimating, you essentially give a weight to different user response. And in this offline hybrid uplifting, you give a weight to user sensitivity of the treatment. By doing a weighted sum of user sensitivity and the user response, you get the final score that measures the value of this treatment. You can determine and look at the distribution of this final score and decide when to apply the treatment. So that's it. That's Kuaishou's uplift modeling for video recommendation. Thanks for watching. I'll see you next time.